Okay, I'm going to do a screencast of problem number 766 on Mastering Physics with the professor sitting on the beam, and explain how to find the tension in the rope and the force of the, I think they also asked for the force of the beam on the professor here. So those are the two things we're trying to find out. So I drew a force diagram here of the beam, and I show the mass. Starting on the left-hand side, I show the force of the hinge, the y and the x components of the force of the hinge, because the hinge does have a force it exerts on the beam. If the wall wasn't there, the whole beam would shoot to the left. So the hinge has to act to the right to offset that. And I'm sure the hinge is also providing an upward component to support the professor and the weight of the beam. So I'm showing those two forces there in their components. That's going to be my axis of rotation when I get to the torque equation on the next slide, but I just want to show you those forces there. And then I show the mass of the beam and its weight right here. I show the force of the professor on the beam right here. I show the tension on the beam right here, and then I break that into components x and y. So those are all our forces. Unfortunately, we have two unknowns there, actually more than that if we include the hinge forces. So we've got, we don't know the tension, we don't know the force of the professor on the beam, because it's not all of his weight is on the beam. He's being partially supported by the tension on the rope. Okay, so let's go to the slide here. Got the same force diagram, and I also have a force diagram here of the professor himself. Okay, so I've had to do that because I need to find a second relationship between the tension in the rope and the force of the professor on the beam, because we need a second equation because we have two unknowns. So in this equation, I'm going to have, I see I lost my force here of the x component. Okay, so I already have a sum of the forces in the y direction for the beam equation over here. And if you notice, I've got the two upward y components. The hinge y component and the tension y component is equal to the force of the professor on the beam going down and the mass of the weight of the beam going down. Those two have to be equal to each other. That doesn't help me too much, so I'm going to have to do a sum of the torque equation for the first force diagram of the beam itself. Then I'm going to come back to the force diagram of the professor in a second. So the sum of the torques has to equal 0 because this thing is in static equilibrium. So I'm going to use this as my axis of rotation. Sorry, let's do this again. This is my axis right here at the hinge. That gets rid of my y component of the hinge force as a contributor to the torque. So I'll have the weight of the beam times its distance away from the axis of rotation. Don't forget to multiply it, and that's a negative one actually. Actually, you know what I'm going to do? I'm just going to have all the counterclockwise ones equal to the clockwise ones. So let's just keep that positive, and I will add to that one, going in the same direction, is the force of the professor on the beam times the same lever arm. Those two together have to be equal to the tension, y component, so times sine of 37, because that's going to be, this component right here is going to be the y component, so the tension times sine 37 times the entire length. Okay? Alright, so I have two unknowns in that equation, this guy here and this guy here, which is difficult. And I also don't know the length, but notice how the length shows up in each one of these terms, so I can divide by L and I can eliminate that. So that's why I had this second force diagram over here, is now I can come over here and I can set up a second equation to relate tension to the force of the professor on the beam. Only notice this is the force of the beam on the professor. But you know Newton's third law, these are a force pair, so the force of the beam on the professor is equal to the force of the professor on the beam, just in the opposite direction. So in this case, I've got the mass of the professor. I don't need to do any sum of the torques, just the sum of the forces in the y direction equals 0. the mass of the professor times G, his weight, is equal to the tension plus the beam on the professor, the normal force. It's actually a normal force. So I should call it that. So that's an N right there. Okay? But these two guys are equal. So if I'm trying to solve for the tension in the beam as one of my possible things I'm trying to solve for, I'm going to rearrange this equation and solve for the normal force of the beam on the professor, and then substitute for that and get rid of it. It's equal to mpg minus t. Now I can substitute that in and solve for the tension in that equation right there. Okay, here's the equation simplified. So I substituted this expression here in for the force of the professor on the beam. I substituted that in from the other equation, and I eliminated the L's because I can divide both sides of the equation by L. So now I have to rearrange this for T, and so I'm just going to multiply both sides by 2 to start with, and have 2T times sine of 37, which is 0.6. Yeah, let's just leave it as sine of 37. How about that? Okay. So let's see. Now it's the mass of the beam and the mass of the professor, which I have both of those. The mass of the beam is 25. Actually, before I start to substitute in, sorry about that, I'm going to solve for T. So what I'll do is mbg plus mpg equals 2t sine 37 plus t. Factor out the t, 2 sine 37 plus 1. So the tension in the rope is going to be the mass of the beam, 25 times 10. Mass of the professor, 71 times G is 10. 2 times sine of 37 plus 1. So the tension in that beam is going to be, I get 435.6 newtons for the tension in the beam, which means that if I can now go to that other equation that asks for the force of the beam on the professor, let me go back and pull that up. Okay, so this equation was, actually we called it a normal force. Normal force of beam on professor is going to be equal to the mass of the professor minus the tension. So that's going to be equal to 71 times 10 minus 435.6. So 710 minus 435.6 is 264.4 newtons, I think. So hopefully that helps you understand how to do number 766.